Section 7.3 adds in the law of cosines. So we spent the last two chapters or two sections talking about the law of sines. This one is going to be for the law of cosines. The law of cosines is sometimes called the general form of Pythagorean theorem because if I, for right now, just like covered up this part, so I'm going to do that, don't do this for yours, but if I covered this up, this one is Pythagorean theorem, right? C squared is equal to a squared plus b squared. However, when we use this with the law of cosines, we can extend Pythagorean theorem to all of the sides instead of just the hypotenuse. So again, Pythagorean theorem is for 90-degree right triangles, and we're working with non-right triangles. So we have this alternative or general form of Pythagorean theorem. So for any triangle with sides A, B, and C, the following hold true. And I want you to highlight a couple things. Right here, these are going to be the sides that you are looking for. And these, notice they're capital letters, so these are angles. So it's important in this one to remember, again, capital letters mean angles, lowercase letters mean sides. According to the law of cosines, the square of a side of a triangle is equal to the sum of the squares of the other two sides. That's the a squared plus b squared part, minus twice the product of those two sides and the cosine of the angle included in between them. So this time, because an angle has to be included in between the sides, we are working with side, angle, side triangles. And we'll be able to extend this to side, 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 but we need it an included angle, so we have to have side, angle, side. That's the information you'd be given this time to use the law of cosines. So let's just jump right into how to use it. So again, this is for side, angle, side triangles and for side, side, side triangles, which we'll see in a second. Example 1 says, a surveyor wishes to find the distance between two inaccessible points, A and B. So they want to find this distance A and B, and for whatever reason, this surveyor can't walk to point A or walk to point B. Maybe there's some like giant trees in the way. I don't know. While standing at point C, she finds that B, so going this direction, is 529 meters, and A, looking this direction, is 423 meters. We've measured that. Angle ACB, so the angle she's standing at, is 132 degrees 40 minutes. Find the distance C. So we want to know the distance across here. We were given information of a side, an included angle, and a side, which tells us we're going to end up using the law of cosines. First things first, because we don't want to use this bit right here, let's change this into just degrees, which we should be pretty good at. That's going to be 132 plus 40 over 60. And because we want to have very specific numbers, we're going to leave that as a fraction when we're using it. We're going to leave it as 398 over 3 degrees. Just, we want degrees. Let me make that look like an actual degree symbol. Okay. What are we looking for in this problem? What does it tell me to find? Side C. So I'm looking at the 3 versions of the formula at the top of your paper, and we're going to use the version that is solved for side C. So the one that we're going to use is C squared equal to A squared plus B squared minus double those two sides, A and B, times the cosine of the included angle, which is big C. Now, just like with the law of sines, especially with this one, because there's a lot of letters floating around here, I recommend deriving the formula first or solving for exactly what you're looking for before you plug numbers in. This way is really easy. If we're looking for C, what do I do over here to get C by itself? Square root. Now, normally when you take a square root, you have to put plus or minus, but we're dealing with distances. Will distance ever be negative? No, so we just need the positive version of this. So this is actually the formula I want to use to figure out that side C. I know every piece of information already in here because I know the side, the included angle, and the side. So if we fill this in, A is labeled to be 423 meters, so we're going to square that. B is labeled to be 259 meters. So we're going to square that. Then we're going to subtract 2 times A times B, so those same numbers again, 423 times 259, all multiplied by the cosine of C, which we found in degrees was 398 divided by 3 degrees. That looks like a 0. Everything is already solved. All I have to do is throw that in a calculator. Now there's a lot to actually calculate. I recommend if you're wanting to do it in parts, do the entire radicand, so the stuff underneath the square root, and then take the square root. Don't try to put it in bits and pieces because there's so much. I would also just type it all at once. So if you type it in all at once and press go on your calculator, it's going to tell you that side C is 628.1008 meters. And that's what we're looking for here. So the law of cosines lets us solve problems when we have side angle sides. We could not use the law of sines here. If you notice in this triangle, there's no complete pair that I know both values for. I don't know both big A or little a, big B little b, or big C little c. So I have to use something else to solve, which means I'm going to use the law of cosines. Questions, comments, concerns. That's just answering one question about a particular triangle. If we go on to the back, we're going to start solving whole triangles, which means we'll find all of the missing pieces. So for example 2, we're going to solve triangle ABC if A is 42.3 degrees, B is 12.9 meters, and C is 15.4 meters. I recommend always drawing a picture so that we know what this triangle looks like as we're using it. So here's A, B, and C. A is 42.3 degrees. Side B, which is across from big B, is 12.9 meters. And side C, which is across from big C, is 15.4 meters. I am given side, angle, side. Side, included angle, side. So my spidey senses are telling me we're probably going to use the law of cosines because I don't have any pairs to use the law of sines. So we can find this side very easily. The reason I know I can find this side is because if I look at the formulas, we know angle A. The only formula on the other side of your page that uses angle A is the version that's solved for little a. Do y'all see that? So I know that I'm going to use the a squared plus b squared, nope, a squared equal, b squared plus c squared minus twice bc times the cosine of a. Whatever side you're looking for is the angle you have. The other letters are the other letters. Now again, if I want to solve for actual A here, I'll start using the correct color. In fact, I'm going to go back. You don't have to erase. I'm just going to write this in the correct color. Okay. To solve for A, we did this on the other side. How do I get A by itself? Square root all of that. I highly recommend deriving the formula first before you start plugging stuff in because things get lost if you're using numbers and deriving at the same time. But we can throw all of this information in here. If I'm looking for A, I will do in my calculator b squared, which is 12.9 squared, plus c squared, which is 15.4 squared, minus 2 times 12.9 times 15.4, all times the cosine of that angle we were given, which is 42.3 degrees. Oof. They're lengthy, but it's one calculation. The only algebra I did was doing the square root. So this A ends up being 10.4738 meters. So voila, we have a part of our triangle. It does ask me to solve the whole triangle, so I am going to have to use this information to continue to find the missing pieces of this triangle. But here's the nice thing. Now that I've added that to my picture, don't I have a complete pair of A and A's? Once I have a complete pair, I can go back to using the law of sines, which is generally easier because it's less chaotic, in my opinion. So to find something else, what we're going to do is we're going to use the law of sines. Now, I know I have to use the sine of A, big A over A, because that's the pair that I have. At this point, you choose whether we're doing B or C. To follow my notes, because that's what I did. We're going to find B first. Also, that's alphabetical order. It feels very organized. This problem will allow me to solve for B. Because I know big A, I know little a, I know little b. So we solve this equation for B. We're going to derive it first. This is A times sine of B. This is B times sine of A. We're going to divide by A on both sides. B times the sine of A over A. To solve for angle B, we take the inverse sine of all of that, so B times the sine of A over A. I'm not worried about there being two triangles. So last class, we were worried about there being two triangles when we did inverse sine, but that's only going to happen for that ambiguous case of side-side angle. Okay? This one, side angle side, will only ever have one triangle. So we don't have to worry about that possibility. That ambiguous case only comes in for side-side angle. Yeah.
Will it be side-side angle if C has the angle?
At the very beginning?
Yeah, if C has the angle, will it be side-side angle?
Correct. So if it wasn't on A, if it was side, side, and then angle, yes. That would be the ambiguous case, so we would have to worry. And in that case, we wouldn't have to use law of sines because we'd have C and C.
It's only side-side angle?
For the ambiguous thing?
Yeah.
Yes. Side angle side is fine, but side angle side requires the law of cosines instead of just the law of sines. But once we're here, we can throw things in. Sine inverse of little b, which is 12.9. Sine of A, which is 42.3 degrees. All divided by A, which is 15.4. Beep, 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 bop. We calculate. We get that angle B is 55.9872 degrees. Yes. Where'd I get that number from? Oh, you're so right.
That's the right number on the screen.
Backing up, this is 10.4738. I thought that was nice. I was like, how the heck did I use all the numbers printed on the paper? You're right. I didn't. I can read.
You wrote the correct number down.
I did. Yep.
It's been a long week.
Yeah, I went to the Stars game last night. It didn't end until 11:25. And I specifically looked because I was like, girl, I'm tired.
Why did you leave early?
Because it was the final game of regular season.
You could have listened
We
to
want-
it on your phone.
We were first seed in the West, y'all. This is a big deal.
You could have listened to it on your phone.
No, I had to be there. It went to a shootout though, so it was like a good game. That's why it went so late. They didn't start on time. It was supposed to start at 8:30. It started at 9:02. Girls watching the clock. Okay. So now if I add this information to my picture, I'm just not going to reach. So this is 55.9872 degrees. I can either make the next part really hard or really easy. What's the missing piece of information from my triangle now?
Angle C.
Angle C. What's the easiest way to find angle C if I know the other two angles? 180 minus the angles. You definitely could do the law of sines again, but why? That's so much work. We can find angle C by doing 180 degrees minus angle A minus angle B, which we have the values of on our paper. Angle A is 42.3 degrees, and angle B we just found to be 55.9872 degrees. We calculate, and that's 81.7128 degrees. And voila, we found all of the information we need for this triangle. So what I love about law of cosines, here's my math brain for a second, it uses all three rules we've used. Law of cosines to start, law of sines in the middle, the law of triangle sums at the end. So many things. Of course, I can't help myself. I'm going to add this to my picture because I like to see things completed. So 81.7128. You don't have to do that. I just like to see things finished. Questions, comments, concerns about the law of cosines for a side angle side triangle? Okay, your next page is a different kind of triangle. It says it in the top, but if you notice in what it's given to you, what information did I give you for this triangle? All three sides. Side, side, side. Which means I have no angle to start with, but I have all of the sides. This is a different kind of triangle. This is our fourth case. We're still going to use the law of cosines for this case. It's just going to look a little different. So if I draw my picture, oof, that's an ugly looking triangle. You get it. Here's A, B, and C. A is across from A. That's 9.47. B is across from B, 15.9. Let me add my units. And C is 21.1 feet. Mathematician's choice at this point of what we find first, and because we're going to follow the notes I did, somehow I found C first. You'd think I'd go in alphabetical order. I did not. But if we're finding C first, big C, flip over your paper to the three formulas. Which formula am I going to use if I want to find big C? Because there's three versions. There's only one that uses big C. Which one is it? The C squared starting one. So if we start with C squared equal to A squared plus B squared minus 2 times AB cosine of big C, I want to find big C. Which means, and this is really, right here is why we derive formulas first, because this one is gnarly. We need to derive this formula or rewrite this formula so that it says big C by itself. I'm going to show a ton of work. You'll probably see a pattern, and you won't have to derive it all later. I'm going to subtract, not with a highlighter. I'm going to subtract A squared and B squared to the other side. Do we feel okay about that? I have moved them from the right side to the left side, both subtracted. Now, I want to get, again, C by itself. C is inside of cosine. So to get C out of cosine, I first have to get cosine by itself. So I'm going to divide both sides by the stuff, very mathematical term, the stuff in front of cosine. So that's negative 2 times A times B. Divide both sides, yes? Now, how do you get the C out of a cosine? Inverse. So we know that angle C is the inverse cosine of C squared minus A squared minus B squared all over negative 2 times A times B. This is the main reason this entire unit I've been having you derive first. This one is crazy if you've plugged numbers in first to find what you're looking for and not lose some numbers as you go. But once we have it all the way solved for C, we just throw things in the formula and throw it in our calculator. That means what we're typing in our calculator is cosine inverse of C, which is 21.1 squared, minus A, which is 9.47 squared, minus B, which is 15.9 squared, all divided by negative 2 times A times B. So 9.47 times 15.9. Woo! But that's one calculation. We derive it with algebra, plug in our values, type one thing in a calculator. Way easier to not make mistakes with your numbers this way. When we press go on a calculator in one fell swoop, so you would type all that in one time, you probably using the fancy fraction, using all those parentheses, we should get that angle C is 109.9435 degrees. Okay. Phew. Law of cosines, check. We add it to our picture because it's way easier to see what we got when we start adding things to our picture. I should have made my triangle bigger so I could fit everything in there, but you win some, you lose some. Cool. What do you notice about my triangle now that I put that red number in there? It's now side angles. Side angle side. Okay, so I could use the law of cosines again, or we have a whole pair. We have big C, little c, right? When we have a pair, what can we use? Law of sines. You totally could use the law of cosines again. In fact, I think I did that once and then realized I was doing too much and erased it and started over. You can, it still works. But since we have a whole pair, we can switch to using the law of sines again. Notice that you have to use the full pair. So I know that I'm doing sine of big C over C. And then it's mathematician's choice of whether you find A or B. Because we're following my paper, I chose to find A first. Sine of big A over A. You could choose to do B first. It doesn't matter. You'll get the same answers because it's the same triangle. Now, what are we looking for again? Specifically what letter? Big A, yeah. So we derive this formula for big A. We cross multiply, that's C times the sine of big A equal to A times the sine of big C. Divide by C on both sides. And then take the inverse sine of both sides. Again, I know that because this is not the ambiguous case, side-side angle, I know all of the sides. There's not going to be two options. We fill in what we know for this angle. We would do sine inverse of A, which is 9.47, times the sine of C, which we just found was 109.9435 degrees, all divided by C, which is 21.1. We calculate in one fell swoop. Oof, I'm already down at the bottom of the paper. It's fine. We're almost done. We get that angle A is 24.9546 degrees. I like to add these to the pictures. Things look nice when they're finished. So this is, bless you, 24.95. Was that not a sneeze? Oh, I take it back. Unbless you. Oh, sorry. I thought that was a full sneeze. Okay, so we can do this the easy way or the hard way. Now that we have two of the three angles, how do we find the third? 180 minus the other two angles. And I'm just going to slide to the side since I already ran out of space, but you probably have some space. We're going to find that angle B would be found by doing 180 degrees minus angle A minus angle C. So we have both those numbers. This is going to be 180 degrees minus angle A, which is 24.9546, minus 109.93. I can't reach that. 5 degrees. Beep, 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 bop. You get that angle B, the final part of this triangle, is 45.1019 degrees. I'm going to move it, but I'll put it back. That means angle B, we found the easy way, not the hard way. Voila. So again, even though this was a different presentation of information, this was side, side, side instead of side, angle, side, I still use the law of cosines, then the law of sines, then the triangle sum theorem. So let's see a little application piece here. Example 4 on the next page says that we're going to find angle B, which is part of this roof truss, which is the name of the thing that like holds a roof up, the triangle that creates a peaked roof, to the nearest degree for the truss shown. So find angle B. What information was I given in this triangle? I was given all the sides. So I know if this wasn't in the notes for law of cosines, I know that when I have all three sides, I'm going to use the law of cosines since I have no pair, angle, and side. Now, which version of the law of cosines am I going to use? The one with the b squared at the beginning. Very good. Okay, so if I have b squared is equal to the other two letters, so a squared plus c squared, subtracted by 2 times those two letters times the cosine of big B. And what are we finding in this question? The angle B. We're designing this roof. We knew how long the wood beam was we used as the ceiling and the joist to make the top. We want to know the angle that we're at to see if like all the snow will slide off of our roof. Those are things that you have to think about when you do construction. I don't do construction, but I know those things. Now we're having to derive this formula for B. So just like we did before, we want big B by itself. We start by moving away the terms that aren't a part of the term with big B. So this is B squared minus A squared minus C squared equal to negative 2AC times the cosine of B. The steps kind of repeat, so after I move those over, what am I doing? Dividing, so I can get cosine by itself. This would be B squared minus A squared minus C squared, all divided by negative 2AC equal to the cosine of B. One step away to getting B by itself. What's that last step? Inverse cosine, yeah, so inverse cosine of all of that, B squared minus A squared minus C squared, all over negative 2AC. And once it's derived for the angle we want, it's very easy to plug in all the information we have, which is all three sides. So angle B would be the inverse cosine of B squared. And if I look at B squared, what number do I use? 6, because across from B is 6. Minus what squared? 11 squared minus what? 9 squared. All over negative 2 times 11 times 9. Calculate. That angle of the roof is 33.0302 degrees. So the law of the law of sines had a specific formula to use, like in those notes the first day of this packet, that was used to find area. It follows from the law of cosines that if you know all three sides, the side, that there's a different formula you can use to find the area of a triangle without having to find any angles, which is pretty cool. And that's called Heron's formula for the area of a triangle. It's specifically, again, for side. To use this formula, you have to have something called a semi-perimeter. Semi means half, like semester is half your school year, right? So you take half of the perimeter. Perimeter is all the sides added up. A semi-perimeter is half of that. If you know all three sides, you can find the semi-perimeter. The area of the triangle is given by the formula area equal to the square root of semi-perimeter times the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. But you're given A, B, and C, so this is really just a calculation problem. There's not anything you're solving for. You're just finding the semi-perimeter, plugging stuff in, and calling it a day. So let's see. Let's use Heron's formula to find the area of something side. All right. It says the distance as the crow flies, so straight lines, from LA to New York is 2,451 miles. From New York to Montreal, Canada is 331 miles, and from Montreal to Los Angeles is 2427 miles. What is the area of the triangular region having these three cities as vertices? We can ignore the curvature of the earth, so we're flat earthers for a second. What this means is we are looking for, let's say this is LA. Okay, here's LA. New York is like across the country, yeah? Here's New York. What's the distance from LA to New York? 2451 miles. If you don't know about the geography of Canada, Canada is more towards New York, which makes sense because it's only 331 miles. So we're going to put in our fake map of the world here, this is going to be Montreal, Canada. What's the distance from Montreal to New York? 331 miles. And then if I'm flying straight from Montreal to LA, that's 2427 miles. So here's my triangle. It's side. I want to find the area of this triangle. If this was in the middle of the ocean, it'd be like finding the area of the like Bermuda Triangle, you know, that place, the scary place we have to worry about, I guess. So we're finding the area of this triangle, but I don't know any angles. It's not a right triangle. I don't have any bearing or anything, so I know I can use the side, side, side Huron's formula. To do this, I first need a semi-perimeter. The semi-perimeter is half of the three sides added together. So I'm just going to add 2451 plus 331 plus 2427, and then take half of that. That means that my semi-perimeter, which I will use in this formula over and over again, is 2604.5 miles. But that's all the information I need to find this area, because the area based on Huron's formula is just all of that plugged in. I'm not even going to write the formula down with letters. We're just going to fill it in because we don't have to solve for anything. But it's going to be a giant square root. The formula says to use the semi-perimeter, so that's the purple number, 2604.5. And I'm going to multiply that by the semi-perimeter, 2604.5, minus the first side length, so that's 2451. Close parentheses. And then the next factor, which is the semi-perimeter, minus the next distance, the next side length. And see, I already ran out of space. I did not make my square root long enough. Multiplied by the semi-perimeter minus the last side length. But that's what I'm looking for. There's no solving. It's just number crunching at this point. I trust we can throw things in a calculator, so we calculate. And this makes sense why this number is going to be ginormic if you're stressed that you got a ginormic number in your calculator. We're talking about the distance pretty much across the United States and kind of into Canada, so it's a pretty big space, is 401,664.1109 square miles. So it's just another formula to use so you don't have to find the height or altitude of the triangle and worry about all of that stuff, which is what you did in geometry class to find the area of triangles. So to put it all together, this very last page here is just kind of a summary page for you on the 4 cases for triangles that we've had so far. So if you're looking to just look one place, it doesn't have formulas on it, but for like, what should I do with this triangle? This might be a good place to look. This is what you were given. You were given 1 side and 2 angles. That's from the first day. It's side angle angle or angle side angle. You would first find the remaining angle using the angle sum formula, which is the idea that the 3 sides, A plus B plus C, have to equal 180 degrees. That's our easy geometry moment. Because you have 2 of the angles, you can very easily find the other one. Then you use the law of sines to find the remaining sides. We had to do the law of sines twice, using the pair that we knew to find the information. Case 2 is our ambiguous case. This is the one that we should pause on because this is where we have side-side angle. There may be no triangle, 1 triangle, or 2 triangles. We first find an angle using the law of sines. Then we find the remaining angle using that angle sum formula. So kind of the backward steps because we needed to find 1 more angle and then solve. Then you find the remaining side using the law of sines again. However, you have to check if 2 triangles exist here. 2 triangles are going to exist if you do 2 things. 180 minus that angle you found. And if the angle you were given plus the angle you just found are less than 180, that's when you're going to have 2 triangles. This is the one that I would pause and take my time on, is when you get side-side angle, because we have to determine if we have 1, 0, or 2 triangles. And if we have 2, we just split our paper in half, find both triangles. Case 3 and 4 we learned about today. Because I was not given two angles or couldn't find two angles quickly, I find the third side using the law of cosines. Then I find the smaller of the two remaining angles using the law of sines. At that point, I will have two angles, so I can go back to that angle sum formula and find the third. That's what we did today. Same thing for side, side, side. It's the same steps basically, that you're going to find the largest angle using the law of cosines, then use law of sines to find that last angle, and then use the angle sum formula to find the last one. So if you're looking for a place in your notes just to summarize the steps you should take, doesn't have formulas on it, I get that, but there's some space down at the bottom if you wanted to write them all there for yourself. This is a good page to have open while you're working. All right, we only have one section left in chapter 7, and it does kind of take a little bit of a left turn because we're going to introduce vectors, but it is still about, I know, all my physics people know vectors. It does involve triangles still, which is why it's in chapter 7. But you have the rest of the class, which is a good amount of time to work on your homework from any section in chapter 7. Remember, chapter 7 homework is due the night before the test, which is not for a while because next week there's another STAR test. So I will see y'all Tuesday next week, and then probably not again until the week after that. Is that right? Do I have that calendar right in my head? Okay. Fabulous. All right, so let's use this time wisely. Let's get our work done so we can really let senioritis take hold in the next couple weeks. But we got to get our work done first. Work first, senioritis second.